All right, you guys, so bear with me as we are all dealing with this new technology and recording a video for one of my first times. But hello, and we are going to talk about theorems and formulas, more specifically the SSS similarity proof and how to find the area of a sector. So first off, we are going to begin with the SSS triangle similarity theorem, which we are going to seek to prove. And basically, as we know, the SSS similarity conjecture, a theorem, or the side-side-side similarity is basically saying that if the three sides of one triangle are proportional to the three sides of another triangle, then both triangles are similar, and we have that highlighted right here. And for this proof, basically, we are going to assume that we have the corresponding angles postulate, which says that corresponding angles that are formed by a parallel line are congruent, and the ASA congruency postulate, which basically says that if you have an angle and another angle and a side in a triangle, that the triangles are congruent. All right, so we're going to move on to this proof right here. So we are going to prove that the side-side-side similarity theorem, if three sides of one triangle are proportional to the three sides of another triangle, then both triangles are similar. So what we're going to have to prove basically is that triangle ABC, which is right here to our right, we're going to prove that it's similar to triangle DEF. So bear with me, you guys. So for our given, which is right here in the blue, we have two triangles, triangle ABC and triangle DEF, with the corresponding sides, AB over DE, which is equal to BC over EF, which is equal to CA over FD. So from looking at this, we know that AB over DE is equal to AC over DF, or as I have it written, CA over FD, because that's a given, so we know that's true. And we can also bring from this that CP over DE is going to be equal to DQ over DF. And we know this because by looking at a little diagram that we have over here, we can substitute these two segments, CP and DQ, for AB and AC. So that would be by substitution. Now we also know that PQ is parallel to EF. Now we know this because we can look at the converse of the basic proportionality theorem, which would say that if we have one line that splits a triangle proportionally, then the line is parallel to the base of the triangle. So from there, we can also take that angle DPQ, which is this top angle, is the same as, wait, hold up, I did that wrong. Oops. It's angle DPQ, sorry, is the same as angle E, or angle DEF. And we know that angle DQP is the same as angle F, or angle DFE. And we know that because of corresponding angles. If we know the lines are parallel, those angles are corresponding. So those angles are going to be the same size. All right. So from there, we can say that triangle DPQ is similar to triangle DEF. And we can say that by the AA similarity, which tells us that if we have two angles in a triangle that is the same as two angles on another triangle, then the triangles are going to be similar. So that is our fifth step that we are doing right here. Sorry, I'm trying to write this out. All right. So moving on, we know that dp over de is going to be equal to pq over ef. And we can bring this out because of the definition of similar triangles. So basically what we're doing is we're putting the corresponding sides. So dp is going to be similar to de, and then pq is going to be similar to ef. Now what we can do from there is that we can substitute, instead of dp, we can put our segment AB, which is from our other smaller triangle over here. And instead of PQ, we can substitute BC. So for these ones, it's a substitution since DP is equal to AB. And then for the same as PQ over EF, we can substitute BC. Since we know that PQ, which is this segment right here, is equal to BC, so we have our segment PQ equal to our segment BC. And we can derive that basically from our last step right here, because these triangles are going to be proven as similar. So we can have a triangle ABC, which is going to also be equal to triangle, that's a very bad triangle, triangle, bear with me, you guys, sorry. It's going to be triangle DPQ, and we already know that triangle DPQ is similar to triangle DEF. So we can derive that triangle ABC is similar to triangle DEF. All right, you guys. I am sorry if that was hard to follow, but in case that was hard to follow, we have come prepared with our proof. So what we did is that we had our triangle AB over DE and AC over DF, which is if that was given. And then from there, we were able to substitute the other two segments from the other triangle, as we see here, since they are corresponding to this triangle. From there, we were basically able to use substitution by looking at the corresponding angles, assuming that we have that parallel auxiliary line, which is coming from the converse of the basic proportionality theorem. Using substitution, we are able to derive other segments that are equal. And then from there, we can figure out that the triangles are there henceforth similar. Thank you for bearing with me, guys. That was a very long explanation, but hopefully it was well understood. Now we're going to move on into how to determine sector areas. So we know that a sector of a circle is basically a section of a pie, you can think of it. If you're cutting a slice of pizza or cutting off a slice of pie, that would basically be like a sector because it is the area between two radii and an arc of a circle. So as you can see it right here, the two radii would be AO and BO, and then the arc AB. Then the formula to find the area of a sector is basically as depicted here. You would take the fraction of the arc measure and divide it by 360. So you would have the arc measure, whatever this angle may be, divided by 360 or divided by the whole circle. And then you would multiply it by the area of the circle, which we know is pi r squared, and you would get the area of a sector. So now what we're going to do is look at this example right here. So we have our A, our arc, which is 45 degrees, and we have our radius, which is 20 centimeters. So the sector is 45 degrees out of 360, which is our A over 360, or 1/8 of the circle if you simplify the fraction. And we're going to multiply that by pi r squared in order to get that fraction of the whole area of the circle. So what we're going to do is we're going to set up our equation, replacing the arc measure, 45, by A, dividing it by 360, and then we're going to do pi r squared, or pi times 20 squared, because 20 is our radius. Once we do that, we're going to simplify the fraction, get 1/8, and we are going to get 400 pi, which, since it's a simple fraction, it's 1/8, you can also just divide 400 pi by 8, and you would get an answer of 50 centimeters pi. All right, so now let's look at some practice problems so we can further understand how to find the area of a sector. Let's look at this first problem, for example. This is our first problem, and it says that the radius, which would be this right here, this would be the radius, is 6 centimeters, and we know that our arc, which is A, is 60 degrees. So we can set up our equation, which is A over 360 times pi r squared. So what we're going to do is that we are going to set up our equation further down here, and we're going to write it in blue so you guys can see. So we are going to have 60 degrees over 360, and we're going to multiply that by pi r squared. And what we're going to do is we know that we can simplify the fraction 60 over 360, and that fraction is going to equal 1/6. So what we're going to do is we can write that out, 1/6 times pi r squared. Now we know that our radius is going to be 6 centimeters, so it would be pi 6 squared. 6 squared is the same as saying 6 times 6, which will mean that our equation will turn into 1/6 times 36 pi. 1/6 would be the same as dividing by 6. So if we could divide 36 pi by 6, we would get an answer of 6 pi centimeters squared. So this is going to be our answer. And of course, if you wanted to be more exact, you could multiply by pi, or 3.14, which would give us roughly an answer of about 18 centimeters squared. But we're going to leave it in terms of pi in order to keep things simple and not work with any decimals. One problem that I would like us to also look at would be 9 and 11. So first, let's look at number 9. So 9 tells us that the shaded area is 12 pi centimeters squared, and it's telling us to find the radius. So we have our equation, which would be that the area of a sector is equal to A over 360 times pi r squared. Now we know what the area is because it tells us that the shaded area is 12 pi centimeters squared. And it also tells us what A is because we know that the arc measure is 120 degrees. So the way we're going to set up our equation this time is on the left-hand side, we're going to write 12 pi is equal to 120 over 360 times pi r squared. What we can do here, first off, in order to get rid of the big numbers, we can simplify our fraction. So that's going to equal 1/3 because we can divide 360 3 times by 120. So we're going to get 1/3 times pi r squared. Now the next thing that we can do in order to get rid of that fraction is that we can multiply by 3, since that's going to cancel out the 1/3. Now we multiply by 3 on both sides, we get 36 pi is equal to pi r squared. Once we have that, what we can do, we see pi on both sides. We can divide by pi, and dividing by pi would basically get rid of it. So what we're left with is 36 is equal to r squared. Now, since 36 is like a full square root, we have no decimals. We can just square root it, and we know the answer by simple math. We find the square root on both sides. We know that 6 centimeters is equal to our radius. And the way we solve that by placing what we knew into the equation, which is right here. Now, one last problem that we're going to look at for today is going to be number 11, which states again that the shaded area is 120 pi centimeters squared. And it gives us the radius this time. So we know that r, which is like right here, r, we know r is equal to 24 centimeters. And we know the area, which is 120 centimeters squared, 120 pi, sorry. So what we are going to do is plug in what we know to our equation. So we know our equation, which is over here, the area of a sector. Area of a sector is equal to A over 360 times pi r squared. We have the area and we have the radius. Now x over here is our variable that is substituting for A, which is the arc measure. We don't know what that is. So what we are going to do is we are going to fill in our equation with what we know and solve for x, or solve for the arc. So what we are going to write is 120 pi is equal to x over 360 times 24 pi squared, or pi, sorry, I said that wrong, pi times 24 squared. Again, what we're going to do in order to get rid of any pesky numbers is to simplify first. So if we square 24, we get 576. So we can write down a new equation, which is 120 pi is equal to x over 360 times pi times 576. Okay, so now what we see, similar to the last problem, we have pi on both sides. In order to not mess with that 3.14, we can divide by pi on both sides, which gets rid of it. Our new equation is going to henceforth be 120 is equal to x over 360 times 576. Now what we're going to do is we're going to divide by 576 on both sides. We're going to divide on this side as well by 576. And what we're going to get if we divide 120 by 576 is 0.208333. So let me write that down for you guys. 0.20833 repeated is equal to x over 360. So now what we can do in order to get rid of this, we're going to multiply by 360. So we're going to do times 360 on both sides. We're going to do times 360. And once we multiply by 360, we get 75 is equal to x. And we know that this is 75 centimeters. So in this problem, we were missing the arc measure. So 75, so then it's not centimeters. Testing that you guys are paying attention. 75 degrees is equal to x, or equal to the arc measure, right here. So in this problem, we were missing the arc measure. Hopefully I didn't confuse you guys anymore. And we learned how to find the area of a sector and how to prove the SSS triangle similarity theorem. Thank you. Hope you guys aren't just confused and that you may have taken something from this video.